This quote really gets to the heart of what we're talking about today. In tech, it feels like we're always chasing the next new shiny thing. But honestly, the most valuable lessons, the ones that stick around, they come from understanding the fundamental principles that just don't change. It's so easy to get distracted by the latest framework, but there's a huge amount to learn by focusing on the core, timeless problems of just working with data.
And that's exactly what we're going to do. Welcome to The Explainer. Today we're unpacking the core ideas from the book Designing Data-Intensive Applications. We're going to get past all the hype and really look at the fundamental principles that power the massive software systems that, let's be honest, we all use every single day.
So, let me kick things off with a question for you. What could your Twitter feed, your Netflix queue, and your online bank account possibly have in common? I mean, on the surface, they do completely different things, right?
The answer is that they're all data-intensive applications. And this is the central idea of the book. For these huge, modern systems, the main challenge isn't a lack of computer power. It's the data itself, the sheer volume of it, how complex it is, and how fast it's always changing. The real bottleneck is the data.
So, if data is the big problem, how do we build systems that can handle it well? Well, that brings us to three fundamental goals. You can think of them as the pillars that define any good data system. Let's break them down.
First up, reliability. And this is so key. Reliability doesn't mean nothing ever goes wrong. Come on, that's a fantasy. It means the system is designed to handle things going wrong. A server crashing, a buggy software update, a human making a mistake. And it just keeps on working correctly anyway. It's designed to anticipate chaos.
Next is scalability. And this is not just some vague idea of handling more users. It's about being specific. How much more load and what kind of load? Is it a million requests a second? For an app like Twitter, a huge challenge was the fan out. When a celebrity tweets, one person writes and suddenly millions of people need to read it, like right now. The point is, you can't build for scale if you don't know exactly what you're scaling for.
And finally, maintainability. I love this one because it's the human pillar. And man, it gets forgotten all the time. You can build the most brilliant, technically perfect system in the world, but if nobody can understand it, run it, or change it without breaking everything, it's a failure. This is about designing systems for the people who will have to live with them for years.
And here's a crucial little distinction the book makes. A fault is when one small part breaks, say a single server's hard drive dies. A failure is when the user actually notices, the website goes down. The whole goal of a reliable, fault-tolerant system is to handle tons of faults without ever having a failure.
Okay, so how do we actually do all this? Let's imagine our app is getting really popular. All of a sudden, we have two massive problems. First, what happens if our main server just dies? And second, what happens when our data gets so big it doesn't even fit on one server anymore? This leads us to two fundamental techniques.
The first solution is replication. It's a beautifully simple idea. To survive a server crash, you just make copies of your data on different machines. Each copy is called a replica. Not only does this give you a backup, but it also lets you handle way more users because you can spread out all the read requests across all those copies.
But what if the dataset itself is just gigantic? I mean, way too big to fit on one disk. The solution for that is partitioning, which you might also hear called sharding. You just split the data into smaller chunks, or partitions, and you spread them out across a whole cluster of machines. Now, no single computer has to hold everything.
Now, how you partition your data is a critical decision, and it comes with major trade-offs. You can partition by key range, and you can think of this like a physical encyclopedia, where volume AB is on one shelf and CD is on another. This is great for scanning ranges, but you risk creating hotspots if everybody suddenly wants data from the S volume. Or you can partition by a hash, which basically scatters the data evenly everywhere. Great for avoiding hotspots, but it makes those efficient range scans nearly impossible.
Okay, so we can now store a huge amount of data reliably across tons of machines. Great, but raw data on its own is pretty useless. The next big challenge is, how do we process that flood of information to actually learn something from it?
So, the classic model for this is something called MapReduce. It might sound complicated, but it's a beautifully simple two-step process. In the map step, you go through all your raw data and just pull out key-value pairs. The classic example is counting words. The key is the word, and the value is just the number 1. Then, in the reduce step, the system gathers up all the values for each key and just aggregates them. It sums up all the ones to give you a final word count. Simple, powerful, and you can run it on a massive scale. MapReduce is a classic example of batch processing. Think of it like doing your laundry. You wait for a full basket, then you wash everything all at once.
The newer way of thinking is stream processing. This is more like washing each dish the moment you're done eating. You're dealing with a never-ending stream of events, processing each one as it arrives in near real time.
Okay, so this brings us to the final and maybe the most mind-bending idea from the book. It asks us to completely reframe how we think about all these different data systems we've been talking about.
What if you looked at your entire organization, with all its different databases, its caches, search indexes, message queues, and you saw it not as a collection of separate systems, but as one single, giant, logical database?
From this perspective, a traditional database is kind of like an all-in-one stereo system from the 90s. You know, it has the CD player, the radio, and the tape deck all in one box. An unbundled approach is more like buying the best turntable, the best amplifier, and the best speakers as separate, specialized components. In this world, event logs like Kafka become the system's central source of truth. Distributed storage becomes the tables, and stream processors act like triggers that react to new data. Each piece does one thing, and it does it really, really well.
And this is the big shift in thinking. When data moves between these systems, it's not just some messy copy-paste job. It's more like the database is automatically keeping itself consistent. You need to create a search index? That's just the database building an index on its own data. You need a cache for faster access? Well, that's just a pre-computed view of the data, what's called a materialized view. It's all one single logical system, constantly updating itself.
We've covered a lot of technical ground, from reliability and replication all the way to stream processing. But the book ends on this really crucial human note. Building these powerful systems isn't just a technical exercise, it carries a profound responsibility.
At the end of the day, data systems are not just abstract collections of bits and bytes. They store information about people, they shape decisions that affect people's lives, and they encode our values. The book leaves us with this final thought. As engineers, we have a duty to think beyond the code and consider the ethical impact of our work. The question isn't just, can we build it, but should we? And what kind of world are we building when